In this video, let's practice a problem related to the energy conservation. We've got a system here with a block and a spring. First, let's visualize exactly what is happening here. The block is moving toward the spring with a specific speed, which is 1 meter per second in this case. The moment it makes contact with the spring begins to compress and pushes back against the block, causing it to slow down, right? Now think about the energy. As the block slows, its kinetic energy decreases. But energy doesn't just disappear. So where does it go? Well, it's actually being transferred into the spring, converting it into elastic potential energy. Eventually, the block loses all its kinetic energy and comes to a momentary stop. And at that exact moment, the spring is compressed as far as it can go. And our goal is to calculate exactly what that maximum distance is. Now, you might be thinking, won't the spring push the block back out? And yes, it absolutely will. But that part is beyond what we need to solve right now. For this specific problem, we are hitting the pause button exactly at that moment of maximum compression, right before the rebound happens. Okay? Alright, since we're assuming the surface is frictionless, we don't have to worry about the energy being lost to friction or heat, right? So all the kinetic energy from the block is transferred directly into the spring's elastic potential energy. Therefore, we can set up our equation simply as Ek equals to Ep. In other words, the kinetic energy lost by the block is exactly equal to the potential energy gained by the spring. Right? Now let's expand these terms using our standard formulas. For the kinetic energy, we have Ek equals to 1 over 2 mv squared. And on the other side, we have the elastic potential energy equals to 1 over 2 multiplied by the spring constant K and the displacement of the spring delta x then squared. So delta x is the displacement or the distance the spring is being compressed from its natural length. Now let's rearrange this to solve for this distance, delta x. Since we have 1/2 appears on both the left and the right, we can just cross it out, right? Next, let's move the spring constant k over to the other side. So by dividing both sides by k, we can get mv squared over k equals to delta x squared. Then simply take the square root to isolate our variable delta x. So we have delta x equals to the square root of mv squared over k. Alright, so the last step is to plug in the values. So we have the mass of the block is 2 kilograms multiplied by the velocity, which is 1 meter per second, then squared over k, which is the spring constant, which is 1,500 Newton per meter. Then we have this root. So the calculation works out to 0.037 meter or 3.7 centimeters.